Okay, so there is one update. Today we have one extra listener here. So the SCAT is going to join our lecture, if you don't mind.
Bring them, bring her with you next time. For the internship.
Could you repeat it again?
I was saying, bring the cat with you for the internship next time.
Well, I'm not sure about that. It's Yegor's cat, the PhD guy. So he just left here, his cat, for a couple of days. Okay, so I think today we're going to talk about linear quadratic regulators, what it is, how to derive them for certain cases, and I will just briefly remind you the formalism of what's going on, and we'll start with a very brief example. And after that, we're going to try to derive basically the LQR, which is the short for linear quadratic regulator. So the topic of today's lecture is this one. Have you heard about this type of controller earlier?
No.
No,
Okay.
Haven't heard about it.
By the way, I can elevate the computer. Do you need that, or it's completely fine?
This is all right for me. Yes.
Okay. So in the servo motors, in the individual servo motors, PID controllers are often used. We are already familiar with them in one way or another. So let me just drive some plots how the PID controller could behave. This is the position where we want to go. This could be our initial position. So it will be our X axis. And depending on the parameters, we can reach this desired position from below. We can do it with some overshoot. But overall, the behavior of the controller or the applied control is the following. So for a certain case like this, it could be a mass spring system. And if we apply force here, we can easily say that the PID controller here will have the following form. X desired or X star or whatever. KD times the first time derivative of X minus K sub I times the integral basically of X. I can write it just straightforward like this. So from time 0 to time t, the current time. So at each instant in time, this controller says that we have to exert a certain force measured in newtons upon this block. And this will result in certain type of dynamics. Probably we will have some oscillations that will eventually lead to the system being stabilized in the proper state. All of you are familiar with this one, or we can talk about that in a little more detail.
Could you go into a bit more detail?
Yeah, okay.
Not really familiar with it.
Sure. So let us describe this system in terms of the state vector. So it will be our x-axis. This axis is the same axis as this one. It's just the plot, x depending on time. So the state vector, it's a vector thing. That's why I'm writing x with a line on top. It's a vector of two components. The first component is x. It's a bit of abuse of notation, but please get used to this because, well, you have to understand what is the state itself and don't confuse it with the coordinate. Is this clear or not? By the way, it would be cool if some of you could turn on the cameras. We'll have a more humanish experience, if you don't mind. So this is our state vector, and it lives in two-dimensional real numbers. So x and x dot. This is basically the coordinate. This is the velocity. And they could be independent. They are basically independent from each other because at any point, the block could have arbitrary high velocity. And otherwise, it could be anywhere and with any velocity. So that's why I'm saying that this state vector of the system lives in plane. And we could formulate the problem of stabilizing this block, of bringing it to a certain state. So we can say that this is x desired, and this is x of the block. So we want to move this block to the left, right? We can formulate this problem as a problem of stabilization. So we can, if the 0 of the x-axis is not in the desired position, we can subtract that and reformulate the problem to a problem of stabilization. It's a common way to do that. It's okay? Please give me feedback. Yeah. Okay. And you don't.
So x decide. So we are trying to apply. If we're trying to calculate the force required, that
right, exactly.
That we can move the block from the current position x to x decide, and also have basically like get it from the current state to the desired state that we want.
Exactly. The current state is some x and some x dot, and the desired state is x desired and 0 as the velocity. We want to stabilize this block in a certain position. Okay, and let us think a bit about those components. The first is called proportional because it's proportional to the deviation of the position from the desired position. And the second is called derivative because it's proportional to the derivative of the coordinate. It's proportional to the speed. Why does it really make sense to do that? Well, it turns out that with this term, we are counteracting the velocity. So if the velocity is very high, with this term, we will act upon the block in the other direction so that the velocity will decrease. And now let us think of the behavior of the system if we have only the proportional term here. Let us try to draw the phase trajectory of the system. So on this axis, we will have x, and here we'll have x dot. It's basically the plane where the state lives. And imagine that we have started in this position, x naught. you can imagine what will happen. So if we are pulling upon this block to one side, outside of the equilibrium, and after that we release the block without any friction, dissipation, it will just start oscillating, right? And the kinetic energy will be transferred to potential energy, and then back to kinetic energy, and so on and so forth. It will just loop. And on the phase trajectory, this will look like a circular trajectory, like this. So let us reflect on that a bit. What is exactly this state? Let us think about that. Here we can see that x is 0, and the x dot has its extremal position. So x dot is here as big as it could get in terms of the amplitude. And it corresponds to the position with the maximal kinetic energy. All of the energy of the system is in the kinetic energy, and the position is 0. So that's basically the point where we want to be. The only problem is that the velocity is not 0 now. So it's basically those regular oscillations, and yeah, it's the same for a mathematical pendulum, really. The phase trajectory is the same. So it's the lowest position for the mathematical pendulum, and it's the equilibrium position for, or not the equilibrium, the desired position for a spring pendulum. However, the speed is not 0. And imagine the following. If you do this with a real system, it will eventually stop because of the friction. And the friction counteracts the velocity. If the velocity is to the right, the friction is to the left at all times, and otherwise as well. So we could imagine that, I will take another marker. If we are, say, here at this position, and x dot is positive, we will act with the friction, we will act so that the energy will become smaller. So dissipation, or the phase trajectory of the pendulum with friction, looks something like this. You have seen those pictures for sure. And if we don't have friction by itself, we can act as if we have friction in the system. That's the point of the differential coefficient over here. And yeah,
how do we determine those coefficients, KD and
how do we determine them? Well, there are options about that. Well, there are automatic tuning methods, but in practice, it's done in the following way. We can observe the trajectory of the system, and if the trajectory of the system looks somehow like this, probably this behavior is suboptimal, and we can increase the P coefficient, the proportional coefficient. If we do that, we can approach the desired position faster. However, if we overdo that, we can overshoot. It will basically mean that we are going too fast, and we are running beyond the desired position. And it could be dangerous if we, say, want to save the motors or something like that. So we can work with the overshoot with the D coefficient. And the last part corresponds to the following. Imagine that we want to stabilize the system in the position where the spring is not relaxed, it's constricted. So imagine that we are in the desired position with a zero velocity. What will happen? Well, the deviation from the desired position is zero. This middle term is zero, and the force is zero. So our controller will not act upon this block, and it will start accelerating far away from the desired position. And that's not cool.
Could you explain that again?
Yeah. So imagine that we are already in the desired position. Our x is the proper one, and we have zero velocity. So the deviation from the desired position is zero. The first term is zero. The velocity is zero, so the second term is zero as well. And if we don't have the last term, the force with which our controller will act upon the block is zero. So we really have to hold this block because the spring is compressed, but we're not doing that. So how could we approach this problem? We can add an integral term. What is that exactly? Well, we can draw the plot of the deviation, right? We can do that. We can plot the deviation from time. Here, well, there's too much going on this plot, so I will add another one. It will be just another x of t. So let this be the desired position. And say we have approached the desired position, and we have somehow reached the vicinity of the desired position. And after that, well, we can't do anything really, because we are acting with some proportional force. Let's say that we're now here. The deviation is kind of small, and we can be stuck statically in the position where k, excuse me, kp times x minus x desired is exactly equal to the spring constant k times the position of the block minus x0, and x0 is the coordinate where the spring is relaxed.
And in that instance, the force would be zero.
Not exactly. So it's a good question. Let's figure it out. This is this red block is the block that has some non-zero deviation to the right. So our controller is acting upon this block to the left. However, the spring is pushing back. And this situation is the case when these two forces cancel out.
And because of that, it'll remain static in the displaced position and not
Exactly.
in the desired one.
Exactly.
Okay.
Yes. And the speed is zero, so this term is zero as well.
Okay.
And this leads to non-zero deviation in terms of the coordinate that we can't do anything about, except for adding some integral term. And what is that exactly? The integral term of the deviation will be equal to the area under this curve. And here you can clearly see that over time, this area will increase, and thus this integral will increase, and the force will increase as well. And eventually the block will start to move to the desired position.
Okay, that makes sense. So from 0 to t x of t, so I'm trying to understand the integral. Like, I understand why we're doing it. So I'm trying to understand how the equation for it. So it goes from.
You mean this one?
Yes. I'm trying to understand. So okay, if it deviates for too long, the force will just keep increasing, and eventually it'll. The force exerted by that because of that term would keep increasing, and it would eventually set it back. And
yeah, what will happen is that as the time goes, the integral term grows, and the force slightly increases slowly over time, which means that the block will move to the left, compressing the spring more and more, but the deviation will decrease over time. So
okay.
it's asymptotic convergence, really. We will never approach the desired position exactly, but we really don't care if we have approached it up to a millimeter or something. We're already there. We can easily be satisfied with that. So this is the concept of PID control. Who of you guys have been working with this one?
I haven't worked with this before, but I would hope to, like sometime.
I have an exam on it tomorrow.
You have an exam on the PID controllers tomorrow?
Digital control systems.
Digital control systems. By the way, what topics do you have there?
They were teaching us about, they started from the basics, Z transform, how to do it, why is it important to do it in discrete, and then they went into the design of state feedback controllers, observers, how to check observability of a system.
Oh, yeah, that's a cool one.
Yeah, and then to make, I think it's used to estimate the position, the estimator, the observer, and we have a project to make like a system model and then create a controller for it.
Which kind of model? Which kind of system?
Car suspension.
Car suspension.
So the input is the suspension's actuator, and then you have the other input, which is the noise, or basically the different levels of street levels, and how it compresses the suspension. But yeah, I have an exam tomorrow on the same topic. That's why when I saw you mention on WhatsApp that you will give a lecture on control, I said okay.
Nice.
That's all. Yeah.
So we have two options. The first option is to code some PID control. However, I did that already. That's what concerns me. At that point, a lot less people were attending. That's how I could put this. I don't remember exactly. It was not during the holy month. I believe it was earlier. But so I was doing the PID, and there are recordings. So I think we can go beyond that. We can do some math and derive the linear quadratic regulator.
Still, I don't know what this is.
Yeah, we can talk about that. That's the topic. So are you okay with that? And guys with the cameras turned off, what do you think? Ahmed, Gorky, what do you think?
Stay with me. I think the guys.
Yes, Mr. Fedor, I'm okay with PID controllers because I'm taking now a course called the Dynamic Systems and Control, where we are studying PID controls.
And what do you think about another type of controller, the linear quadratic regulator that is for different applications? So I will try to draw a line between the PID and the other one.
I'm actually still not familiar with this linear quadratic, but I'll try to focus with you.
Okay. And Gorky Ma is writing, I'm in geophysics. You can ask questions if that is comfortable. So let's try to decide. There are a few of us, so let's do some democracy together. What do you want more? New controller that is completely unfamiliar, but it's cool, I promise. Or the good old PID that is cool as well, but it's just different. So what do you think? The linear quadratic is, I could say that it's really more applicable for higher or dimensional systems.
So is it more responsive? Is it easier to design? What's the catch?
It is a controller that accounts for the model of the system. So it needs the state transfer function. We have to understand the dynamics of the system. The cool thing about PID is that you can tune it by just measuring the output. You don't really need to know exactly what's going on in the system. So it could have some friction, it could have some non-linearities, it could have anything. And you can tune it by just knowing what's going on after you have applied a certain controller, especially in simulation. However, it is difficult to formulate this controller for it to optimize some kind of objective, which is really important if you want to, say, minimize energy. In PID control, we don't really talk much about energy consumption, or we don't talk about higher dimensional systems. We can really design a PID controller for each and every dimension separately, but that's not cool in some cases. If we want to, say, stabilize a spherical pendulum, we cannot just cancel out all the cross terms. We can't do that with we cannot do that effectively with the PID control. And if we want to save our effort, if we want to minimize the energy consumption, we have to consider something that is, so to say, thinking up to a certain horizon, or even infinite horizon in the case of the LQR that I was planning to present today. So if you don't mind, we can derive the linear quadratic regulator.
Agree with me.
Okay, so I propose to do a short 5-minute break, and after that we'll dive deeply into deriving stuff. If something is not clear, please interrupt me, and it'll be fine. If you are not into math, I mean, some of you are not into math, that's fine, because you can ask about anything that you can see here. So
Okay.
let's get back in 5 minutes.
All right.
Okay, so let us continue. There is a message in the chat. I wish you recommend some books. Well, I can say that I can recommend any graduate level book on control, really, because we are dealing with the basic concepts, and they are explained in all the textbooks on YouTube. If you want to dive deeper into the control of robots and linear quadratic regulators, other regulators, I can recommend you the following book: Interactive Robotics by Russell T. Drake. However, with the concept of PID, you can familiarize yourself on YouTube. That's absolutely fine. There are plenty of awesome lectures over there. So what are the drawbacks of the PID controller? It cannot account for any type of optimality of our control. If we want to say save effort, conserve energy, I mean, minimize the consumption, how can we do that with the PID? PID is just reacting to the current state of the system. And we can elevate the performance of the controller by counting by incorporating the model of the system into our considerations. So linear quadratic regulator. I would ask to interrupt me at any point if you don't get anything. So it's my fault if you don't understand stuff. So please let me know. We're going to consider the following systems. Their state, I will omit the vector. It will belong to a vector space, n-dimensional vector space. And the behavior of the system will be described by the following vector system of differential equations. Ax plus bu. This vector over here is the control, u. It, in general case, could have some other dimensionality, say m. And matrix A has to be a matrix of n times n, because this vector, n by 1, has to be multiplied by this matrix, and we'll have to get another vector of the same dimensions, n by 1. So A has to be a matrix of n by n elements. And B has to be a matrix of, could you help me with this one? What should be the dimensionality of the matrix B here?
If U is a vector of n, then the matrix B should have also m cross n. I'm sorry, I'm unsure. Like, it's been a while since I've learned about matrices.
So we can spend some time reflecting on that. There's no problem. So no rush, no hurry. It's all good. We're just thinking.
Also, X here, state of the system, right?
Exactly. Yes. Gokima says that I think same. Not really, because let's see. So the vector U has the dimensionality of M times 1, and this matrix B, well, we don't know yet, but first we'll have to be able to multiply this matrix by this vector. So here, the dimension should be the same as here, right?
Okay.
And in the end, we will have to have this as a vector of the height n, right? For us to be able to add it up to this vector. So I'm saying that this matrix B has to have the dimensionality of n times m, where n is the number of rows and m is the number of columns. So we will have to multiply it by this vector row by row. First, the first row with all the vector, then the second row with all the vector, the third with all the vector, and so on. And as a result, we will get a vector of dimensions n times 1. Is it okay?
Yes.
Great. So after we have that, let us try to define some kind of criteria of optimality for the control that we're trying to perform. And also
X dot here is
the
how
time
are we
derivative.
taking the time derivative of the state. I mean,
Yes.
I
Yes.
mean, like, so isn't okay.
Like this.
Okay. So if you're considering the state as the position and velocity, then in this case, X dot would be like velocity and acceleration.
Yes, exactly. Exactly. You're right. We can keep the same example with pendulum if you would like to. So we can just do it manually in parallel. Should I?
That's fine. Either is fine. Whichever would be easy to explain.
Okay, so we can keep in mind this example. Let me just quickly draw it. This is the block, and well, we can start with the case where 0 is here, and we want to stabilize the block to this position, and the spring is relaxed in this exact position as well. The only problem is that it could oscillate because we don't have any friction over here. The state will be, allow me some abuse of notation again, I guess. Okay, so let it be, I don't know, position, whatever, position. So it will be P and P dot. What can we say about the dynamics of the system? We know that M times the second derivative of the position, P double dot, is equal to the sum of all the forces that act upon this guy. And the only force that is acting upon this block is the force that comes from the spring with elasticity K. And K will be positive, the stiffness, the stiffness basically. So let's suppose that we have moved the block to the left. What will happen? The spring will compress and it will start acting to the right. So the force exerted onto the block from the spring will be equal to minus K P, just the position. This is the Newton's second law, so that's fine. And we would like to express this dynamics of the system in the form that I'm going to write over here. X dot is equal to AX. There's no control yet. The block is just moving around by itself. That's fine. So this is a vector of dimensionality 2. This is 2 by 2, and this is 2. Okay, so the only thing that is missing is the matrix A. Let us find it. And as you said, oh, sorry. So X dot is equal to d by dt of x, which is equal to d by dt element-wise of p and p dot, and it will be equal to p dot, p double dot. So it turns out that we have to express this vector p dot, p double dot in the following form. Here we're going to have some matrix 2 by 2, and here we're going to have our state vector p dot. So we'll have to figure out the 4 values of this matrix. Guys, is this clear?
Yeah.
Anyone else?
I do have a question afterwards, after you finish this part.
We can talk about it now if you feel like doing so.
It will make everything.
It's on the separate topic?
It's not separate. It's about how do we model a system basically with multiple input, multiple output, but you have a derivation in the input.
You have what in input?
So the input is derivated.
So you have the controller.
I have like a system in mind. I'll give you an example. But because doing it right now, it will disrupt this example.
Okay. So we can talk about that later. No problem. Apart from that, it's clear. Okay. Goki, Ahmed, Aziz, do you have any comments, questions?
No, that's clear.
Okay. I will repeat that time after time, but please interrupt me if something is not clear. Unfortunately, I'm not.
Something is not clear, we will interrupt you.
Yeah, sure. Unfortunately, I'm not in Khalifa in person. That would be better because we can, interact more freely. But anyway, we will use the visual channel. So let us try to think of what will happen if we multiply those 2 matrices. Do you have an idea of how are we supposed to fill in those elements, those 4 elements?
Would the first column be 0,1?
Right, exactly. Right. 0, 0, 1. Why so? Because if we multiply the first row by this vector, it will be equal to 0 times p, 1 times p dot. That's exactly p over here. That's correct. That's right. And let us think about this second row. So is there any dependency on p dot in
No.
here or no? Well, I can rewrite this thing for clarity. So p dot is equal to minus k over m.
This is p for position?
Yes. P is the position, exactly. We just renamed the position from x to p in order to not confuse ourselves for clarity. I usually get some comments on that because I usually write things like this: x is equal to x dot. People say that it's not clear, and I think I have to write it.
Because displacement is both x, so it will cause issues.
Well, Yeah. So if we're deriving some long formulas, which will happen here, we'll use X, okay, just for convenience. And here we have a specific example, so it will be the position. Okay, so this is the exact expression for P double dot. Is there any dependence on P dot? No, there's not. So the corresponding coefficient over here will be equal to 0. And this coefficient will be equal to minus k over m. And this is our matrix A. And it guides the behavior of our system. Not guides, it describes. The laws of physics guide the behavior of the system. And this is our model that is describing the dynamics. So if we numerically integrate or analytically integrate this thing, if we propagate the behavior of the system to the future, we will actually get an accurate enough prediction up to the model of how the system will behave. So that's just for context. And here we have one more additional term. It's the control matrix and the control itself, the U vector. Probably our control is supposed to depend on the state, right? We're not considering any type of observers, Kalman filters, nothing like that. No noise, no delay, nothing. We want to derive the optimal controller under ideal circumstances. We can relax certain requirements later. And now we can say that we instantly observe the state and we have to react somehow. So you are, I don't know, driving a car or something, and you see exactly where you are, where you go, and what do you want to do. So one of the convenient ways of setting up a controller is in the following form. U, the control vector, could be equal to minus some gain matrix K times the state vector, X.
How do we determine K?
Yeah, that's a good question.
The pole placement?
One of the ways to do so is pole placement, right? That's a good one. We are going to do that in a different manner. We are going to derive this K to find the K out of the optimality in a certain sense. So up to this point, it's all clear and good, right?
Mm-hmm.
Awesome. So now I'm going to formulate the objective. I'm going to state what are we going to minimize. And what I propose to minimize is the following thing. It will be an integral. J, it will be cost, I think. The integral cost from 0 to infinity of the following thing. X of t transpose times some matrix Q, X of t plus U transpose of t R U of t. Ah, there's a cat here again. It's walking around. The integral by dt. So linear corresponds to the type of the system that we're dealing with. We're dealing with linear systems. And quadratic corresponds to the cost function that we are minimizing. Well, and regulator is regulator. It's pretty clear. So if we omit the dependence on time, let's assume that it's clear. Okay, so I will write it in more compact form. Integral from 0 to infinity, x transpose q x plus u transpose r u dt. It's just the same thing, but in compact form. Do you see where the squares are and what basically happens here? Let's try to make sense of this functional.
These squares.
Yeah, so both terms here are squares in terms of x and u respectively. And why? Hmm?
What do you mean by squares?
It's x transpose times some matrix times x. So if we
You mean it's a square matrix?
no. Let's suppose that, well, I'll draw it here. Our vector x is x1 something xn, and the Q matrix over here.
Eigenvectors?
No, not eigenvectors. So it's a matrix of size n by n in order for it to be multipliable by x and x transpose. And what will happen if we write that in expanded form? What is that exactly? So it's the x vector times the matrix times the x vector here, but here it's transposed, right? So imagine that we have our Q in the simplest form possible. It could be an identity matrix of size n by n. So just 1, 1, 1. Here we have x1, xn, x1, xn. What will happen after the multiplication? Let us think about that.
Okay, so the first multiplication would give you x1 0 0 0 0. Then it would just be a diagonal matrix with x1 x2.
You mean the first multiplication, this vector, the row by identity?
I meant the x, like qx.
But Q is an identity matrix here.
So
identity times x will be equal to x.
Yeah. Oh, yeah. Right.
Yeah. So we can write it here as just x transpose times x, or it's multiplication.
And then that times x1 squared plus
right,
x2
exactly.
squared. Okay.
Right. x1, xn, and these vectors will multiply so that in the end we'll have a scalar that is equal to x1 squared plus squares up to xn squared. And this is the simplest case possible within identity matrix. With non-identity matrix, but with diagonal matrix, if say we have some elements d1, d2, we'll have just the same thing but weighted. So d1 times x1 squared, d2 times x2 squared, dn times xn squared. And if we have a general case matrix, well, not almost general case, okay, just some matrix Q, we will have all the cross terms over here as well. But still, we will have some coefficient times x1 square. And all the elements here could be represented by a coefficient times x sub I, x sub j. So this form is quadratic in terms of the vector x. And the same for the second term over here, which is quadratic, but in terms of the u vector, the control vector. And quadratic forms are good because we can minimize them by differentiating. And also, if we want to minimize the deviation from a certain desired trajectory, quadratic cost or quadratic loss or quadratic function that grows quadratically is good for us, because the further we deviate from the optimal trajectory, the higher the cost goes.
But
yeah.
You were saying before that you need to know more about the model for this type of controller. Is it because you need the state variables?
We need the state variables and also the A and B matrices here. Then this is exactly the model. We have to know it. We are not usually supposed to choose it, because this is the characteristic of the system dynamics. It depends on the mass, and this depends on the elasticity, the stiffness. And the B matrix is the control matrix. It's the thing that represents how do we control the system. If you're an aerospace engineer, you cannot really come to Boeing and say, hey guys, let's add 3 more thrusters. You can say that. That is, give you the B matrix and say, hey, this is the system, please control it. So we have to know that more or less precise. That's a topic for further discussion. But if we suppose that we know these matrices exactly, then we can derive a controller that will be optimal in terms of these weight matrices. Now, guys, please pay attention, because we have to state the problem properly. It's kind of difficult. Let us try to understand it entirely, completely. Why do I call these matrices weight matrices? Because if I increase these values on the diagonal, the cost will increase, right? And if I will assign D1 to be 10 and D2 to be, say, 1, the cost will increase more if X deviates from the desired position, not X dot. So with changing these values, we change what our controller is trying to minimize. Does it make sense?
Yes. Yeah.
And the same logic goes with
so
the relation.
We are just in the simple case of a diagonal matrix here. So
yeah.
It's like
the intuition is like this. Well, the cross terms. What do cross terms mean? The cross terms penalize the behavior of, let's say, me being at non-zero coordinate and going with non-zero velocity. In such a case, a cross term will be positive. And let's uncover the relation between Q and R. If both of them are diagonal and the values over here are very big and the values over here are very small, it basically means that we value the minimization of the deviation much more than we value the minimization of the effort, of the energy or power consumption. Does it make sense? Guys, are you here? Are you with me?
Yes.
Yes, yes, Mr. Widow.
So do you have an intuition on what's going on with those matrices? Do you get the idea behind them or not really? So if not, please somehow guide me where to start, what to do with them. Is it clear or okay, so Gokima understands. Who else understands and who doesn't? We're not anyways, we're not in hurry. That's not for grades or anything. We just have to understand this properly. So
could you repeat after the diagonal matrix? My laptop ran out of charge and I got
got it. So I'm saying that the relation between Q and R will influence what do we value more, the deviation of the state from the desired state over time, or the control effort.
Okay.
So if the values of Q are very big and values of R are very small, it means that we do not try to minimize the control. We're running around like crazy, and we just want to approach certain state, and that's it, no matter what. And otherwise, if the values of the matrix Q are quite low and the values in the matrix R are very high, we are hibernating. We want to save the energy, like your laptop, and we halt some processes, we close the browser, we decrease the brightness. We're very careful about the energy consumption. That's the intuition. So with these matrices, with their relation, we balance what do we value more, control or the deviation from the state. And with the internals, we can describe what do we want from our controller. So what is more important for us, to approach the position or to have a certain speed, say? What do we value more? We value
I have a
more...
question, Mr. Rashidor.
Yeah.
What if they are both important, both equally important to us? How can we decide the value that we should put for both functions?
So you have to somehow choose the exact weight. That's really a multi-criteria optimization. It's the same as the student that is studying towards an exam. So the student has to learn stuff, but still they need to sleep and eat and, I don't know, have a rest. So both of these things are important. So you have to choose the balance. And depending on the parameters, the exact output of the controller will be different. If you value, say, if the student is lazy, the values here will be very big. So the student will save effort, but will not approach the state of, I don't know, passing the exam. It's just the end. So we'll have to those parameters are really up to some kind of tuning, but it's very different from tuning the PID control, because here we tune our functional, our cost. We say that we well, if we're dealing with, say, vacuum cleaner, robotic vacuum cleaner, and we know that it's is moving linearly with very high velocity, and it's rotating very slowly. Well, we would like to save some effort with the rotation because it takes a lot of time and it's boring and tedious, and I don't know, motors wear out or something, or it's differential drive, right? So if the robot is rotating, the tires are slipping, so we'll have to repair them. That's why the cost could be higher than the cost of linear transportation. And we as control engineers have to set these values for them to make sense. It doesn't make sense to set this to be an identity matrix and this to be an identity times 10 to the power of 6. It's like we're not saving effort at all. We have to balance stuff. And the same goes with even more high-level controllers like the strategy controller in robotic football. Of course, we want to score the goal, but we don't want to push the opponents. We don't want to break the robot. We don't want to kick the judge. We have to design our controllers wisely so that they approach the desired state and not break stuff along the way.
Do you use PID or do you use something more complicated? Because I know for the servos you are using PID, but more.
Yeah, that's a very good and deep question. That's a topic for another discussion. But what I have to say is that on different levels of control, very different approaches are used. Why so? Because let's imagine that you are planning ahead a series of passes and kicks. So the robots have to pass the ball somehow. And this planning ahead could be up to, I don't know, 20 seconds or something. The scheduler of our robots, the control loop, runs with a frequency of around 180 times per second. So it will be an enormous horizon. We cannot plan ahead up to that horizon with anything reasonable. So in order for us to properly plan ahead to such high horizons, we have to set a relatively big time step. And also we have to simplify our model because we cannot propagate the full model of the robot, 26-dimensional system, into the future. That's not possible. And it will be very imprecise. It will be very time consuming, so we don't need that. Let alone the fact that the noises will, because of the butterfly effect, the noises will lead to our system approaching different state. So we can go along with a much simpler part of the state, like X, Y, and theta. And this is exactly what is used. So in the scale of the field and in the scale of seconds and tenths of seconds, our robot is described as a system with only 3 coordinates, with no velocities. So the whole X is, the whole state vector is X, Y, and theta, and that's enough. So with that, we can plan ahead some kind of ball approach or pass or whatever else with the help of algorithms that do not take into account any system dynamics. We usually do it with graph searches. So there is a map, there are obstacles that we have to avoid, we draw some edges, and then run Dijkstra.
Like a linear optimizer?
Not linear, because the obstacles they could be non-convex.
Yeah, it's not linear, but it's similar to how you just put the equations of the limits and you find where everything will basically intersect.
Well, we are using graph searches. You know that the graphs, right? The concept of graphs. Yeah. So this is the desired position. This is the robot position, and here is some Raban robot. There's some MRL robot, and there is some StarKit robot, and you want to score a goal, avoiding all of these robots. What we can do is we can spread a number of points here, here, and on the circumference of the obstacles. And we can add some edges between all the points, or between the points, so that those edges do not intersect the obstacles. It means that you can pass by this edge. This edge doesn't intersect with the obstacles, this one. So you can go along here. And this one as well, this one as well, but this one doesn't lead anywhere. Okay, it could lead here, whatever. So there are a few options. And after that, we run some kind of, well, not some kind of, just the graph search, Dijkstra's algorithm. And it will give us something like this. So it will be the shortest path.
Yeah, I know it. You will start looking at the grid next to you and then the one next to you. And today we had an exam on that.
You have a lot of exams.
But for wireless networks, it wasn't for, that's why I was confused. How is it applied? It's how to draw the shortest path between networks, between sensors.
Right, it's the same thing. The same thing. Graph searches are very widely used everywhere in, I don't know, for drivers, for robots, for wireless networks, for anything. Graphs are everywhere. Graphs are everywhere. Linear spaces are everywhere.
There's also like shortest path. You can use the same like path algorithm and same what's it called? Search algorithms, like greedy forward. What's it called? When it looks for the point that is the most close to the destination.
It's like A star.
I will check the name right now. I have it.
Okay.
It's like just like you said. What's the equation you said? Dixon something.
Dijkstra.
Yeah. Let me check. It was in localization routing. Sorry. But yeah, it makes sense. But you're placing the points randomly based on distribution.
The first point is the robot. The second point is the desired position, and the other points. Well, if this is an obstacle, we can add 8 points on the obstacle with some additional margin, and it will work out.
Okay.
So 8 points per each obstacle. The number of obstacles rarely exceed, say, 3, 4. There are up to 8 robots on the field and one judge. But more often than not, there are like 6 robots because one is broken and one is absent, and the judge doesn't disturb much. They usually know what they're doing. So, and also we cut this process of considering obstacles by half of the field, because if something is very distant that doesn't concern us much, the situation will change before we get there. So 3-4 obstacles, 24 or 32 points, and 2 points here. And this graph search works pretty rapidly, like tens of milliseconds, really, on this CPU. It's pretty fine because this horizon is very long in terms of, horizon in terms of the time. It's short in terms of the number of steps, but it's looking quite far ahead in terms of the time, like 15 seconds ahead, 20 seconds ahead, and it's okay. And it takes 20-30 milliseconds to calculate that. So this is the highest level of control. The next level of control is well, there are options. It could be center of mass, motion planning. It could be combined with foot placement. I'm saying that there are options because it depends on the quadruped, biped. Different bipeds and quadrupeds use different planning, and you can buy a dog for $2,000 Unitree, you can program it to do anything. I think your university either has one or will have one, that's for sure. Because those dogs, they're very cool. They're very dynamic, and eventually you will see them running around. So anyways, you will have to place your feet somehow. It could be called foot placement or
In your
gate
case,
scheduling or something.
in your case, this is for path planning, and then
This is
Yes.
path planning, and after that, in
Case of,
in Sakharov,
in the case of the RoboCup, so essentially we find the path. Basically, we are formulating this. We are figuring out this path using the points, and we're telling the robot to pass the ball along these paths essentially to the goal.
to walk
Is
them.
no, this is
the dots.
this is not the trajectory of the ball. This is the trajectory of the robot. So this is a approach
Okay.
with obstacle avoidance. It will approach a certain point. If the ball is over here, we have to approach it.
Okay.
And ball planning the path for the ball is a different thing, but it could be formulated in the same terms.
Okay.
So after we have planned the high level path for the robot, it has to follow this path. And in Sakhar robots, it is done with so-called walk engine. Walk engine is the level of control, the intermediate level of control that takes this trajectory, this desired trajectory as an input, and outputs the steps that the robot has to perform. It has basically 3 types of steps: forward, which is the same as backward, basically, but with different sign of the speed. Side step and rotation. Well, I mean, it can go along the curves. So generally speaking, the command could be formulated as Vx, Vy, and omega. If we are considering the robot to be a holonomic platform, it's fine to use this kind of abstraction. We're just commanding the robot to move slightly to the front, more to the left, and rotate, and it will do something like this. So yeah, its lateral speed is pretty low. That's why it goes mostly straightforward. Well, humans do the same. It's not that convenient to go along the street laterally. We basically do the same intuitively. And after the intermediate level of control, we have the lower, the next one, level of control. There we have reference frames and splines. Well, you've seen that already.
But
And
yeah.
After that level of control, we have the lowest level of control, which is PIDs that I have already raised, but PIDs in each of the servo motors. And that's the whole pipeline. Well, on top of that, there could be some planning for the team. It is present, but it's more heuristic than formally derived. So if there are 2 our robots and 1 opponent, we can pass the ball or something like that. So that's more common sense than formal derivation.
Yeah,
And
maybe it will not be very accurate, the model we create.
Yes, and the problem of strategy itself, it could be very appealing to start working on that, but it's a problem, not like Goldbach's problem, not a problem of millennia, but it's very difficult. And at times it happens so that freshman students that come into the team, they ask what to do, and they are getting asked, what do you want to do? And then they ask what options are there, and the options are like kicking the ball, planning the fall recovery, maybe some vision, training neural networks, then are long, boring, difficult options, and then team strategy. And they think like, hey, team strategy, I can play football myself. What could be easier than to transfer this logic to the robot? And then comes the horrible part, because it's a bad problem. It's not only difficult, it's difficult in terms of how to measure the performance. If you are programming car suspension, you can say that the suspension is performing well enough if the car is not shaking. You can measure the accelerations, and it will be a result that you can present, like, I don't know, 5 something. The jerk, the third derivative of the coordinate vertical, is limited to, say, 0.5 meters per second to the third. Okay, that's measurable. That's okay. And you know how to measure that with gyroscope, with an accelerometer. And how can we measure the performance of the strategy? Is it playing against the empty field, or is it playing against the same team with the previous strategy, or is it playing with the code of the different team? Where are we supposed to get the code? What will happen if there are 3 players instead of 2? So it's difficult to measure the performance. And all the options that I have mentioned really make sense, all of them. And how to choose one over another. So it's difficult to formulate the criteria. That's because it's a bad problem. It's like, you please go somewhere and do something. And you ask, what exactly? Well, and they say, do something. It's not clearly formulated. So strategy is it's very difficult.
Maybe it's to make it more robust. So make it not very specific, tailored to one thing, but like the way you guys do it, you're making it work on its own. You're teaching it how to work, not just for RoboCup, but in general, how to get up. And now you're telling me sometimes the opponents are not. Maybe we plan it for 3 players, 2 players, and it's not the same as expected. But if it was a very, let's say, very smart system, it will not depend on these things. It will only depend on its own performance. So don't like measure the metric based on how many goals or how much speed it has or whatever. Maybe just how reliable it is.
That's a good option. That's a good option. But measuring reliability is difficult as well. I'm not saying that you're wrong, but it's difficult just to measure the robustness, the overall performance against who, in what circumstances, about the number of the players. Yes, for sure. But team play when you have 4 robots is very different to the team play when you have 1 robot. 1 robot should be more conservative. It has to save the goal. However, it has to attack somehow, because otherwise it will just get its goal kicked and that's it. And at some point, it will lose. And 3 robots, well, I mean, yeah, this is a difficult problem, because it could depend on the number of the agents, on the exact kind of the opponent. And the robustness that you have mentioned is achieved with, well, all the artificial intelligence here is the number of ifs. And nothing really works better than that at this point.
So
it's
would
the
you
sad
like train
truth.
a model? Would you like train a model, for example, assign train a model trying to get the model to, for example, like get the ball closer to the opponent's goal, or like penalize the ball being further away from, like penalize the model for keeping the ball closer to our goal, or like award the model for getting a score, like and train a model that way. Is that what you guys do?
Like what you're saying makes sense a lot. It's just very difficult to do in terms of, well, it's done now in terms of the reinforcement learning. And Google have published a paper quite recently, maybe half a year ago, about an agent, end-to-end agent, that is playing football against the same basically agent. And what they do is they have 1 versus 1 game. They have external vision. So their ball has markers, and they have external vision. The robots, the agents, are provided with the quite exact coordinates of the ball, about the coordinates of the opponent, about their own coordinate, and it's 1 against 1. It's a very impressive paper, but it's in its formulation, in the formulation of the problem, it's much easier than the RoboCup statement. I think, and I believe that the RoboCup problem at its current state cannot be solved in the end-to-end fashion. If all the data scientists of the world will converge and spend, I don't know, $100 billion, for sure they will do it in a year or something. But there's no urge in doing so. And steadily and slowly, we are moving in that direction. We have a student, a master student, that is trying to reproduce this paper. If he will manage to do that, it will be a very impressive master thesis, because he will reproduce Google's result, being on his own. Well, not on his own. I mean, he is the main guy in this project, so it will be cool. At this point, we don't use strategy level reinforcement learning. We don't do that. We have used trainable agents in kicking the ball. Our ex-captain did that in his master thesis, but it was not robust enough. It was not really better than, so to say, hard-coded kicking. So learnable agents are cool, but they are not always better than traditional control-based controllers. And on the other hand, we have to know all the basics. We have to know that in order to design the training, the goals, and all of that stuff.
It's resource intensive, I think, also to run everything on AI.
Yeah, that's true. We don't lack the computational powers. On board, we have Intel Core i7 and 16 gigabytes of RAM. But that's not a server or something. So yeah, we have to keep the models lightweight, like this model.
This is better than robot dogs.
Sure, right. Its fur is coming out because of the spring. Okay, so how do you feel? Are you tired?
A little bit.
Okay.
Yes, because I have not slept since yesterday.
Oh, really?
Yeah. We're finishing the semester, so we have to push to finish the exams. But that's it. After that, we are done.
So you're going to sleep today, or you're going to study very long?
I have digital control tomorrow. I have to study.
Good luck.
Yeah, good luck indeed. I know the feeling.
Thank you. Yeah, I don't remember last time I slept. So maybe after tonight, when I'm more free, Fedor will see me even more, because right now Fedor is not. I think nobody comes to the lab this week or last week. Come to the lab.
But Fedor is going to Moscow right now. He's in mid-air, and I'm using his account, by the way.
Yeah, I saw the name. I was confused. Fedor. Yeah. So
got to see Fedor last week for the workshop. Yeah, the linear interpolation, and we were learning the.
Yeah, I wasn't there because before that it was only me. He was enjoying the room. He had like you know, he put his legs on the table. He took he has juice. He's enjoying it's really like fun to see him. And he keeps asking me like, are they coming next week? I'm telling him, yes, of course. We were planning tours.
Okay. That's in his character.
Yeah, he was Well,
I'm glad
But-
there are a lot of levels of abstraction here, like because like I'm completely new to this, so I'm glad that there. But I would love to peel back the lesson, like as we're doing right now, just learn more. But I think it's going to take a lot of time, like especially because I don't have the formal math background yet, the formal math or like physics background. So I'm
you
looking
don't
forward.
need, just try to apply it.
Mhm.
Later on, when we have the actual robot on hand, I think this is best because in the internship, when I was with them, when they were teaching us computer vision, the theoretical part, we were not understanding anything. And then we will try to do it, and we can see, oh, this is what he meant by matrices and how to manipulate them or whatever. So because now you're studying just the board itself, you're looking at shapes, numbers. I don't think there's a single number on the board. It's all just symbols.
Well, there is one here.
Yeah, this doesn't count. So other than that, it will become easier.
Is there an
Yeah.
internship this summer? Like, is there a,
Internship? Yes, we'll do the same. Well, we'll not do the same. We'll do better because
Yeah,
we've been learning to teach for a year, 1 year more. So yeah, we'll do that. We'll come in, I believe, end of June. Let me check. Let me double check that because that's important. Hold on, just a sec.
I would love to
Check.
like stop by and learn like in person with, over the summer. That would be really, really nice.
Sure.
it's very tough, but it's very nice.
Mhm.
Okay,
We were
where's the chat? Where's the
5
chat?
days a week from 9 to 4.
Hmm.
But there was a long break like in between. I think it was 2 hours or 3 hours.
I believe if I take the summer, like if I take courses over the summer, classes would end around 1 p.m. So after that, I would have the rest of the day to.
You can attend unofficially. Like some people used to come just to learn from the lectures and just go back home, I guess.
It
Plus,
will be from June 6th.
June 6th. Okay.
Yeah.
Because they bring you chocolate.
Hmm?
I'm telling him they will bring you chocolate, like the one you bought.
And by the way, it will be for 1.5 months. And after that, all of us are going to RoboCup, I believe. Or not all, I'm not sure. But I think all of you, right? Or not? What did Professor Hamad tell you about that?
He is
There'll be a
still
competition
deciding.
in July, right?
I think they're looking for sponsors for now because it's very expensive. And once we find the sponsors, either way, we are working on the robot in the lab. This is what they said. So if we don't participate in the Netherlands competition, we can have it ready for another competition later on.
Yeah.
At the,
Well,
at least. Just
I hope that you will have your first competition because that's a week of horrible sleep and continuous learning. After that, you will wake up another man.
yeah, I know. Last month I was in a competition.
Yeah.
That's, yeah, I was in the US. It was three days I didn't sleep. Yeah, because
Well,
we are.
you're young, but you have to keep an eye on that. It's not cool to do it.
I know, but we had problems because we went all of this way to the US and then our plane crashed, the one for the competition. So
What?
we were fixing it all night. Next day we fly it, it crashes again. We fix it. Third time we fly it, it's there's an issue with it. We fix it. So after we finish all of this, we went back to the hotel. We slept maybe for like 12 hours, 15. It was good.
Yeah.
But it's enjoyable.
Sure. Yeah, we've had a competition recently in Taiwan. It was very tough, but that was cool.
Yeah, I think it's more you manage easier than us probably because it's not the first time, right?
Sure. Yeah.
You don't do the same mistakes again.
Well, we do new mistakes.
They're better than repeating old mistakes.
Oh yeah, that's true. That's true. We have managed to make the robot do the archery with the moving target, and we have a second place in archery this time. So yeah, that's fine. With a lot of other competitions, we have difficulties with walking. Well, without walking, you can't do much. But the algorithms were performing, I should say, good enough, and the team it satisfies me in terms of the communication and overall combination of areas where people are competent at. So the team is really good at this point. It has grown like 3 times since I'm in the team, and it's awesome. There are lots of students.
But yeah, too many
So,
people combining ideas.
We can have a short break and then we'll get back and continue this stuff. Or how much are you into, or how much are you tired? So please tell me.
Not about being tired, because I have to go now just to practice for the final exam, and because it's very early tomorrow, and it's already 8, so I need to finish like in 2 hours, 3. So I will. This is recorded, so I will get back to it where we left off. It doesn't look very difficult. I'm already going to work on the state space representation of the digital control systems, all that stuff, but not the quadratic. So I'll get back to the lecture.
Okay.
Probably.
Okay. So you're leaving now or later?
Yeah, now I think it's better. But let me know if you need anything else from me, anything I can help with, that stuff.
It would be cool if I would ask all of the students who attend to perform some kind of home assignment, and all of you can gather and exchange ideas and help each other. So if you specifically are into control engineering at this point already, you can help people out, and you can gather in the lab or in the library. I don't know. I mean, just to know each other, because you will have to. I was sleeping with a guy from my team in one bed because there were no rooms with 2 beds in Korea in 2019. So you can get pretty close to each other, even in physical sense.
No,
Not that close, I would say, but okay.
So you want us to sleep in the same bed, or do the inside?
Well, you can start from the home assignment, and then it depends on how it goes. Well, usually that's not the case. Usually we have separate beds on the competitions, but there.
I'm joking with you. It's I'm pretty sure it will happen. Not like sleeping in the same bed, but I get what you mean. That it will become there is no barriers. It's fine. But for this task, I think we will need just this couple of days, because the exams, they will conclude like everything, I think, by next week. All of us.
On 16th of May, I think. Final exams will end.
Officially 16th of May, but afterwards there is nothing except for those who are taking internal.
Okay, so all of you are having some kind of exams right now, right? And you are going to finish. Then I propose to do the following. I propose to stop at this point with the lecture, but I will ask you to do the following thing at home in Jupyter Notebook, I believe, or somewhere else. So let us consider this system and try to stabilize it. Try to drive it to 0 in terms of the coordinate and velocity. So you have this block, you can set the mass to say 25 and the stiffness to whatever, it's not important. And the position of the spring when it's free, I mean not compressed, should correspond to the 0 position of the block. Then please implement the dynamics of the system, and what it will look like in Python is roughly the following. So block will be an instance of a class block. Here are some parameters, and then for iteration number, or for I in range iter num, something like this. And here we will have to do the following. First, it's the system dynamics. X dot is equal to, and then you will have to calculate this matrix multiplication. You'll have to obtain the time derivative of the state vector. Right? You follow?
Yeah.
Okay. After that, the second thing, you will have to integrate this using Euler's method. So we're dealing with the discrete approximation of the system, not with the real continuous system. And we can say that X will be equal to X plus X dot times dt. dt could be, I don't know, 0.01 or something like that.
Mm-hmm.
This is just the simulation. So this is the first part. The second part is implementing the controller. So I will write it with a green marker. So you have access to the real state, so you can calculate the control or the force, and it will be PID, some kind of controller from the full state. You will have to implement full state feedback. I don't know. I don't have any specific recommendations on choosing those parameters. Please try out for yourself. Just try. It doesn't cost anything. You will not break your computer if you say if you set wrong values, so nothing will happen. Please try out just different values and see what happens. Observe all those overshoots. I mean, this kind of behavior, diverging behavior, whatever. Try setting positive differential feedback. The system will just accelerate towards infinity, but you will make sense of this behavior. So it will become clear what coefficient corresponds to what. If you will set a proportional coefficient to be 0.01, the system will slowly converge, but it will converge in, well, very long time. That's not cool. So try to experiment with mostly these two coefficients. The integral coefficient could be set to 0 because there is, in this exact case, there is no static friction, no constant offset, but you can try out its problem, say 2 star. If you want to complicate your life, you can try to stabilize this pendulum in this position. So that's totally doable, and you can try. It's not like required or something, but you can try. That's a lot of fun as well. You can try tuning the I controller, the I coefficient. And the third part is please implement the cost calculation. The cost calculation is the following thing. The discrete analog of this integral is basically this. So 0, and here we have x sub I plus 1 transpose q x I sub 1 plus u sub I transpose r u sub I. You can choose Q and R matrices for yourself. The simplest way to do that is just take identities. So with calculating the value, you will get a single, so to say, cost of the state action trajectory of this thing. How bad was the behavior of the system in terms of the deviation, the velocity deviation from zero, and in terms of the control effort, the joules of energy or liters of petrol or whatever, or the liquid oxygen, if that's closer to aerospace. So with this, and it's the problem number 3, with this, you will get the single value, which will represent the cost of the state action trajectory. Here, each word is important. Cost of the state action trajectory. So the state trajectory is the sequence of the states, and action trajectory is the sequence of actions. And we, by calculating this whole sum, will get a single value that will characterize how good or bad does the exact controller with the exact values of coefficients perform. And you can try out different values of P, D, and I and compare them in terms of the cost. You get the idea, right?
Yeah.
So you set certain cost, and then you try to find out P and D so that they minimize this cost. And you can try this for a couple of different costs, like very big cost for deviation or very big cost for control. If you have very big cost for control, your agent, your controller should be lazy, and it's supposed to approach the desired position very slowly. So probably D will have to be big enough because we penalize velocity. Right? No. No. Sorry. No. Both values will be low because we will penalize the exertion of any force. Yeah, sorry for that. I have almost confused you. So with high values of the control effort, the resultant control will be low. And please try it for yourself. So set up the simulation, try out different costs, and it will be cool if you can discuss that in private or in chat or however you would like it to do. And next week, what we're going to do is we are going to finally start deriving this thing. And the point of the linear quadratic regulator is that after we derive it one time, we can then insert in the formula the values of Q and R, and we will get the exact value of the gain matrix such that it will minimize the cost. That's the point. So we can once derive the formula, and then we can change the costs. We can think like, today I feel like I want to save some more energy in the controller. You insert U weight matrices, bam, you have the gain matrix with that. So it's a very general thing. And tuning PID is tedious and it's just time consuming. It consumes your time as a control engineer. If we don't have models, load model, we will have to use PID, that's for sure. Like servos, they just have to hold the position no matter what. We don't know exactly the torques that will have to be applied. And the PIDs are very fast. They could be tuned just once. They guarantee global stability. So there are options. And if you just don't know what will happen, you'll probably better use PID. You can use pole placement, something like that. The classics of the classics. And if you want to minimize some effort, if you want to balance different types of stabilization, I mean, along one axis or along another axis, then you will have to consider the minimization of certain cost functionals. So is it okay with the home assignment?
Could you please upload a description of the home assignment in the WhatsApp group or in the chat so we can return to it anytime?
Yeah,
You
sure.
know what I mean? Instead of seeing the recording again or
Yeah.
trying to comprehend.
Hmm.
I
By the
also
way,
want to ask you a question.
Huh?
Can
Yeah.
we do it through MATLAB and Simulink?
It's a tool that is widely used in engineering, and you're right that you have mentioned that. However, let us try to do it by hand in Python.
Because I haven't used Python before. I'm familiar with MATLAB, but Python, I don't know.
It's a pretty straightforward language to write with. So if you don't mind, we can try learning Python along the way.
Okay.
So, guys, who of you can help Ahmed to install Python interpreter, or maybe
No,
show
I can,
how to use? You can do it. You can do it.
I
Or
can install it myself. No problem.
okay. So I think it's better to have some kind of collaboration. So if you can help your peers out, that would be cool. And if you can gather somewhere and just work on the home assignment, it will be cool as well. And Ahmad, can I ask you to write the home assignment in the chat, please?
So, okay. Can you give it to me? Just let me write it. So basically, it is to design a state full state controller, and then design a quadratic linear. What was it?
So the first part is set up a simulation with the Spring Mass system. Second, try out PID control with different parameters. And third, implement cost calculation.
Okay. So
You
set
can
up.
add you can add certain things from your side if you feel like adding some comments.
I also want to ask, when is it due? When do we have to finish it?
Is it okay to do it in a week? What do you think?
I think we need a week after the finals, or maybe 5 days or something after 16, because I won't work on it these 2 days or 3 days since I have finals.
Okay, got it. The rest of the guys, you're really the same, right? So you'll be learning towards the exam mostly.
Yeah. So you said set up the Spring Mass simulation, design a controller.
Yeah, just a PID, and try out different parameters.
Controller and play with the parameters. I can.
Yeah, exactly.
And then set up cost calculation.
Yeah, quadratic cost calculation in this form. So Q will be a 2x2 matrix, R will be a 1x1 matrix, just a scalar. The next time we will talk about the derivation of the controller, and we will talk about the characteristics of those matrices. We will require Q matrix to be a positive semi-definite. Could be written like this. And R matrix has to be positive definite for our results to make sense. But that's for the next time. By positive definite, I mean that for any vector x, x transpose times r times x is greater than 0 for non-zero vector x. That's
positive.
Well, yeah. Basically, on a level of making sense, it means that we cannot mine some gasoline by, I don't know, doing anything with our engine. We cannot charge our battery by exerting any forces. Any effort will cost us something. That's the meaning of that.
So I wrote set up Spring mass system simulation, design PID controller and play with the parameters, set up quadratic cost calculation.
Yeah.
Do I add more description?
I think you can discuss it with the rest of the team. Is it clear or is it not? Don't you mind if they will just ask your questions about that?
Yeah, I don't mind.
Yeah,
always-
so yeah, that will be awesome. If something is not clear, you can tell me or whatever. So I'm here to help you anyhow. I mean, I'm just trying to stimulate some kind of cooperation. I don't know, that's not the best time to do so because you have exams, but anyways.
Eventually we will, once we finish and we get to meet up more, we will have to work together. So it's
Right.
inevitable.
Right.
So hopefully we will be working together closely.
Inshallah.
Inshallah, yeah, exactly. Other than that, we are more than happy to be in your lectures.
Thanks.
Keep it.
Okay, thank you for coming. I will upload the recording to YouTube and see you next week at the same time. Any questions, direct messages or chat, or ask Ahmad or ask each other. So see you then. Have a nice evening. And
Have a nice evening.
good luck with the exams.
Much appreciated.
Thank you so much. Thank you.
Bye-bye.
Goodbye.